It's Monday morning, and Sarah, a newly hired analyst, just got handed a USB drive containing 10,000 unread customer reviews. Her manager needs them sorted into positive and negative piles by Friday. Reading 10,000 reviews by hand would take a full work week. Naturally, the first instinct is to write a traditional computer program to filter the text automatically. In traditional programming, you have to write the rules yourself. You might tell the computer, scan every review, and if it contains the word terrible, put it in the negative bin. But watch what happens when a customer writes, terrible shipping, but the product itself is fine. The strict rule sees the word terrible and drops a perfectly happy product review straight into the negative pile. Human language is messy. It relies on context, sarcasm, and nuance. If you try to hand code a specific rule for every possible edge case, you end up playing an endless game of whack-a-mole. Machine learning solves this by flipping the process upside down. Instead of a human writing the rules, you give the computer a massive pile of examples, and the computer figures out the rules on its own. This approach splits into 3 branches: supervised, unsupervised, and reinforcement learning. For Sarah's project, we need supervised learning. Here, the model studies historical data, with correct answers attached, learning the patterns to predict answers for new, unseen data. To hit that Friday deadline, Sarah needs a system built to recognize complex language patterns across thousands of examples, far beyond what any string of manual if-then statements could catch. By Thursday afternoon, the heavy lifting is actually done. Sarah didn't even have to build an algorithm from scratch. She pulled a pre-trained model that had already studied millions of sentences, and it processed all 10,000 reviews in about an hour. This chart shows the workflow of a real machine learning project. Beginners expect the algorithm to be the entire job, but in reality, 60 to 70% of the timeline is consumed by the first 3 steps: framing, collection, and cleaning. Step 1 is framing. You must weigh the costs, miss a real complaint, or flag a happy customer as angry. Steps 2 and 3 are collection and cleaning. Real-world data is messy. You hunt down duplicates, fix formatting, and delete blank text entries. Feeding messy, unframed data into a perfect algorithm will simply generate a highly efficient wrong answer. Once the data is clean, we hit steps 4 and 5, training and evaluation. The model spits out its predictions, but we still need human oversight to check those predictions against reality. Sarah pulls a random sample of 15 reviews, grades them herself, and compares her answers to the machine's. The model only agrees with her about 73% of the time. When we look closely at the misses, a pattern emerges. The model struggles with edge cases, like reviews that say, fits great, but the color faded quickly. It's a 50-50 split of positive and negative sentiment, which easily confuses a binary classifier. To handle this, the model assigns a confidence score to every prediction. If it's unsure about a mixed review, it flags that output with a low score, signaling that a human needs to step in. The purpose of the evaluation step is to map the exact boundaries of where the machine fails, allowing human judgment to cover the gaps. That brings us to steps 6 and 7, deploy and monitor. In a professional environment, a machine learning model serves as a living pipeline integrated directly into the company's daily workflow. This graph shows what happens to a model after deployment. Over a 12-month period, the accuracy slowly drifts downward. As consumer vocabulary and cultural context naturally evolve, the data shifts and the model's performance decays. But for Sarah, it's finally Friday morning. She walks into her manager's office, delivers a clear breakdown of the 10,000 reviews, and the presentation is a success. Sarah met her deadline by focusing on the human side of the process, framing the right question, scrubbing the data, and rigorously evaluating the edge cases. Then, management asks one lingering question. We see the numbers, but how sure are we that they are actually right? Generating a prediction immediately creates a new requirement. You now have to measure the uncertainty of that prediction. And to do that, you need an entirely different set of tools: the science of probability and statistics.